Hello. Okay, let's get going. Number 131, palindrome partitioning medium. Given a string S, partition S such that every substring of the partition is a palindrome. Return all possible palindrome partitionings of S. Partition S so that every substring of the partition. Okay. So if S is AAB, partitioning it so that it's split into every letter means each of these partitions or each of these substrings is a palindrome because A backwards is A. AA backwards is AA. Okay, so find every way to split S so that all the pieces of the split are palindromes. Let's start the timer. All right, so there's one obvious way to do this, which is try every possible splitting. Check if they're all palindromes. This is going to be every possible splitting is an exponential number of splittings, 2 to the n. Checking if something is a palindrome costs n, because you have to look through the whole string, and the string, well, I guess this goes away because the string is, well, it doesn't matter. This is too slow. This is very slow. I mean, it might be the best way to do it, but we'll keep thinking of ways that are faster than this because usually an exponential algorithm is not the way. I'm trying to think of some kind of pointer solution. So we starting from the left, we keep going right until we've found a palindrome, and then we output that, and then we keep searching right. That's not gonna work though, because we have to remember too many things. We have to remember like whether we've split or not in an exponential number of ways to return all the outputs. So now I'm thinking recursive. Basically, is there a way to construct the answer for a string given the answer for the string minus the final letter in the string? And kind of, but it's a little hard to think of. It's like, let's say my string is this. I guess one of the problems is if my string is this, I can have an exponential sized answer because like one of the answers is going to be a, etc. One of the answers is going to be a, etc. And then one of them is going to be like this. One of them is going to be like this. Then you're going to have like a. So there's an exponential space requirement just for the output. So maybe exponential, I guess that means I shouldn't dismiss an exponential solution because it's going to have to be exponential anyway. So we could start with the very first idea of just checking every possible split. The thing is, there's a very obvious shortcut, which is you don't have to if the string is if one of your substrings is already not a palindrome, you don't have to keep checking the rest of the splits. So directly iterating over the list of possible splits is probably not the right way to go, because then you can't shortcut once you've found a piece of a split that's already impossible. So I still think recursion is the right way. So like obvious base case is if length of S is 1, then then you split it, then the only palindrome you can make out of it is this. And then the recursive case is just try every single split, as in like every split where you've only split it one time, and then recurse on both halves. 0 to 1 times. Or you can say 1 time, but one of the allowed splits is after the end of the list. So I'll add a second base case if not S, return just an empty list. In other words, if length of S equals 0. Does that make sense? So I'm trying like, you know, what if we split it right here and then recurse on this side, recurse on this side? What if we split it right here, recurse on this side, recurse on this side? Now the other way you could do a recursive thing is just only ever split on the, well, it wouldn't be a split. It would be like, let's say I have the answer to this and I have the answer to this. Can I make the answer to this? And I'm not sure if you can. I am not sure if you can. So I'm gonna go with my first idea. All right. So for I in range S, for everywhere you can split S, I'm actually going to do S plus 1 because I also want to include, well, that's not how you do it. This should be the length of S. And I'm going to do plus 1 because I also want to include splitting after the end, in other words, not splitting. So we're going to do partition S up to I. We're going to partition S starting at I. And then how do you make a result out of this? You have to multiply these two together. Like every one of the solutions in here is the beginning to every one of the solutions in here. So we're taking like a Cartesian product of the two things. So let's say ret is an empty list. For left in this, for right in this, ret.append left plus right. And then at the end, return ret. Oh, and then oh, you know what? Yeah, if I'm doing +1, then my answer is not necessarily shrinking. The other thing is I'm not even checking if anything's a palindrome. So why don't we keep that like that? So these are the ones where the answer size is shrinking and you combine them together. And then we add an extra one, which is if the whole thing itself is a palindrome, then also include that. So if S equals, reversed S, let's just do reversed S. I actually don't know if that's allowed. Let's try in a little sandbox. String of reversed of ABC. No. But probably if I casted it to a list first, it would work. Not quite. What if instead of using reversed, I used the alien face operator? That returns a string right away. Okay. So the alien face operator is I'm taking a slice of S and I'm saying it starts at the beginning, it goes to the end. That's because I haven't specified a beginning and an end. And it goes by -1 each time. So that means I'm going to iterate backwards, basically. So this means it's a string. Then ret.append S itself. Also, it shouldn't be S itself. It should be a list that includes S. Okay. So for AAB, we got this answer, and we got this answer, but we got duplicates. Why do we get duplicates? Because we got duplicates because we recursed on this with a split here, and we recursed on this with a split here, which is the same thing. So how do we prevent duplicates? Like, there's one way to do it is to turn the thing into a set. I mean, you can't directly do that because you have lists, so you'd have to also change the way you're storing stuff and then convert it to lists at the end. But that's not the best way, because the other way is iterate over, only iterate over the stuff that you want. So don't even give it an opportunity to be a duplicate. How would I do that though? The other thing I just realized is I'm not doing the thing I said I would do, which is shortcutting when you are already not possible. So I might as well just iterate over every possible splitting and check if they're palindromes. I wonder if I should just be doing that, because I'm not using the sub answers to speed up my search at all. And now that I'm looking at the code, I'm not sure how I would. So let's take a break from this for a second, and try to do the dumb iterating answer. So for I in range 2 to the power of length of s, I want this to be -1 because there's one fewer splits than there are letters in the string. If you think about what I'm iterating over, I is an n-1 digit number. I can interpret its binary representation. Sorry, not n-1 digits, n-1 binary digits, n-1 bits. I can interpret each bit as encoding yes, there's a split here versus no, there's no split here. So I can construct my string or my partition as iterating over the bits of I. So for bit in let me try to write it a different way. So the bits of I is what I care about. I know that there are this many of them, so I'm going to do this for I'll call it B. I think actually I'm going to call this N. I'm going to call this I. And then the bit is going to be equal to N bit shifted to the right by I, and all of that bitwised and with a 1. So if you think about the number, let's say it's all zeros except there's a 1 in this position, and I'm looking for this position. This is 1, 2, 3, 4, 5, 6, 7 bits to the it's the 7th bit in the number. So if I shift it to the right by 7, 1, 2, 3, 4, 5, 6, or I guess by 6, I mean, then it, and you know, maybe we have other random bits in the number, but I've shifted the number right by 6. So now it's the least significant bit. And now if I AND this with 1, 1 is like this number. So if I AND it with 1, I end up with this if this was a 1, and this if this was a 0. So this is how you extract a single bit out of a n-bit number. So if there's a bit, if that is a 1, there's a split here. So partition dot append the string, the remainder of the string up to this. So let's make a variable here for remainder that starts as the full string. At this point, you grab remainder up to I, and you remove that from the string. Remainder equals remainder starting at I. So this should generate every partition. Let's see. Ret equals this. Let's just put everything in ret just to see that it is generating everything. Ret.append partition. It should give the wrong answer, but it should include every partition. And it did not. Not even close. So what am I doing wrong? Am I wrong about the -1? Is that, oops. That helps. Oh, one thing I'm thinking, I'm forgetting is I also have to add, after I'm done iterating, whatever's left in remainder still needs to go into partition. Okay, this looks more like it. I've got a bunch of empty strings. Is the -1 thing not correct? Okay, the -1 thing is correct. It's because there is one fewer splits than there are characters. Now my only problem is empty strings at the beginning. Do I just need to start the splitting at 1? That's better. I have duplicates. That's kind of confusing. It's probably because I'm starting the split at 1, so it's skipping. So that there's going to be 2 of everything because I'm skipping the first digit, and that means there's going to be a solution where the first digit was 0 and a solution where the first digit was 1. Why am I skipping the first digit? It's because when I is 0, then the splits happen. Then the split is like before the first character. So let's not start at 1. Let's just treat I equals 0 as the first as the character, as the split after the first character. So that would be replacing all these i's with I. That's hard to do like that. Just I plus 1. And then it looks like I'm going to have to do length minus 2 to get back to doing as many answers as I wanted. Or no? No, maybe not. I'm still ending up with duplicates. And I'm guessing that's because I'm doing one too many splits, and one of the splits, or actually I'm not sure. Why don't we print binary representation of I and just look at what we have and think about it in here. It's always a 1-digit thing. That's not right, because I want it to be, there should be 2 splits in a 3-letter word. So maybe my -1 was not the right thing to do. Okay, now it's 2 digits at least. So for AAB, why am I repeating I? It's because binary of I is not what I care about. Binary of N is what I care about. I is just the position inside the string. So let's go back to -1 because that's what makes sense to me. Okay, N is a 2-digit number, 2-binary digit number. Here we're saying no split anywhere. Actually, while we're going through, show me the current partition as you go. So yeah, there should be, with 0, there should be no splitting. With 1, there should have been a splitting at I equals 0. Because this you shouldn't have. This is still the right thing to check. It's just that if it represents splitting 1 later, you can do that there. You can do that in the right place in the string, but you still have to mathematically like grab the correct digit. And this now looks right, except for the trailing empty string. But we can just not add that so only add the trailing thing that hasn't been added yet if we still have stuff to consume. Okay, now this is every splitting. With duplicates. How did we get duplicates again? Oh, because of the... It has something to do with this remainder thing. Something I want to understand is which n's are printing which partition, are causing which partitions. Let's remove our other print statement. So 0, and actually give me the binary representation of n so that I can see the digits of it. No splits gives this. That's right. Split on the right gives this. That's confusing. No. This would be split on the left, because I have to read the digits from right to left, basically. So a 1 in the first slot means a split in the first place. So that's what this gives. 1, 0 means don't split on the first place. So this is no split. And then split on the second place. So AAB. 1, 1 is supposed to be split in both positions. So it should be A, B as separate things. So why is that not happening? Why is that not happening? So 1, 1 is our problem. Why aren't we splitting here? So I would be equal to Oh. Yeah, yeah. Well, here it's saying I is equal to 1. Right, right. But then we do plus 1. So here we should be splitting at position 1 because it's 0 plus 1. Here we should be splitting at position 2 because it's 0 plus 2. Just to check. So if I have AAB starting at 2, that should be B. Oh. I think this plus 1 trick, I only actually want to do that on the first. Oh, this is confusing. I only want to do that the first time because after that I've trimmed the string. How do I say that? I guess the way to say that is to trim it by 1 less. No, that doesn't work. The plus 1 thing is really confusing me. It's because the issue is if I have AAB and I grab it starting from 0, or up to 0, that's going to be an empty string. So I want to grab it up to 1 for the first, if there's a split in the first position. And then the remainder would be that. So that's if I is 0, I want to split it like that. But then I have this. And now I is a bigger number. Okay, this is the problem, actually. I'm treating I like it's an index into the full string, but I've trimmed the string, so it's not the full string anymore. So instead of trimming the string, let's just remember what the last split was. So we go from last split to I. And then we don't do any remainder stuff. We just remember that last split was I. Yes, we don't have remainders anymore. We just have S. And then we do still have to do this, but the logic is different. Now this is append from last everything after last split. Maybe we don't need this +1 anymore. No, we're still gonna need it because partition Python AAB or ABC from 0 to 0 is an empty string. So we still want to go one farther. I think we need this +1 here too. Perfect. Okay. Now this was supposed to be the easy part, but it took us a really long time. This is every possible split. Now we can trim the ones that don't have a that aren't palindromes. So this is, there's a word for this, which is substring. Substring equals this. If substring is not equal to substring backwards, then break, because, or yeah. The thing I want to do is like skip this n, but that's hard to do because I would want to break out of the first loop and continue out of the second loop. Which I can do. I'm just trying to think of a clean way to do it. It would be like well, it's actually, so I'm not gonna break right now. I'm just going to what do I want to do? Because we can actually skip more than just n. We can skip all of the n's that have this prefix, because it's like we already know that there's no split, that splitting here doesn't work. We don't have to check all of the zeros and ones in the string that comes later. I'm just trying to think of a clean way to do this, because now we've got weird nesting of stuff. So if I make a little helper function, def partitions or split, yeah, partitions that takes a string. We've already got a string in the global scope, or in the local scope. And it takes an integer which is the binary encoding of the partitions. This would return a list of strings. This is just called a partition. So let's just say get partition. And that does this thing. End this and returns partition. And then it doesn't break here. It like raises an exception. Not a palindrome. So then this just does this, get partition end. Partition equals get partition. Try that, accept. Continue. So I think this will give us the right answer, but we can do better. And obviously last split needs to go in here. So does partition. Oh, I have to do the same thing over here. Substring equals this. Here's something I'm thinking. Could I just iterate over one more digit than there are, so that last one will always be 0? So I don't have to have a special case to append the end? No. If it's 0, that won't work. It would have to be 1. So I'd have to do I plus one left shifted by len of s, which is also the same thing as 2 to the n of s, or plus equals, I mean, to add an extra 1 at the beginning so that so that I'm always appending the extra split. It's not I that I have to add that to, it's n. That works. That's so hard to read, but that works. To add 1 extra split so that I don't have to handle it as a separate case after I'm done. The problem is some of this stuff is not a palindrome, but I'm not failing. Why? What if I don't have the try except? Why am I never raising an exception? Substring is this thing. We're only appending substrings. To partition. So how do we ever end up with a partition that has stuff that's not a substring? Like AAAB. Also, this is not right, because now I'm doing it too often. I have to do it only once. I just don't understand how the exception is not being raised. I just don't understand. Python ABC not equal to ABC backwards. True. Equal to ABC backwards. False. So why would this not get called? Is there something weird with Leetcode that, no? If I print the substrings, only the A's are ever substrings. What about B's? How are they ending up in the answer? Oh, I'm still doing this. I meant to stop doing that and to use the trick. The trick with the extra one on the end to do that. But that trick is not working, so print bin of n. Oh, it's just one too many. It's so I just needed a -1. Okay, perfect. Get rid of our prints. The exceptions are good. This should now give the correct answer. Good. Okay, before we submit, we can speed this up because we have more information here than just not a palindrome. We also know that every n with the same digits of I up digits up to I is also going to fail. So we can skip, like, that would mean we could skip ahead further. Unfortunately, we are going through the digits backwards, which means we can't skip ahead because it's the least significant digits that we've just decided are a problem. So if we changed it to go through them forwards and the most significant digits we've decided are a problem, then we could skip over the least significant digits and go to the next candidate. So that means first we have to iterate through the digits of n the other way around. Which means so it means the most significant digit of n must correspond to the split on the left. Hold on, is it actually symmetrical and it doesn't matter which way I'm going? The most significant digit, so you've got like A, B, B, C, C, whatever, and then you've got a number and it tells you where you're splitting. Right now, this corresponds to splitting here. What I would like, well, that's okay. It doesn't matter whether the backwards are, it doesn't matter whether you're splitting the string backwards or forwards. It just matters that once we found a problem with this part, we don't need to check all the rest of the numbers in here. We can just increment this part by 1 and keep looking in our search space. But we're not finding a problem with this part because we're splitting the string like we could. It's just that we're doing the string in the wrong order. Or we're iterating over the i's in the wrong order, basically. So I think if I just reversed this, this should give the same answer. It does not give the same answer. So then we would be starting with the most significant digit. Well, I guess at that point, just to make it easier to understand, let's just make that split to the first letter. So split is going to be equal to len of s minus I. And then all of these places where I've got I, let's replace that with split. we replace that with split. Let's get rid of this for a second so that we're just generating every answer. Looks like we're kind of close. So split starts at we're going reverse. So we start up here, and that means split here. So we go backwards from len of s. I think I'm just missing like a -1 or a +1. So the last split starts at 0. This is so close. Oh, I think actually this trick doesn't work anymore. Now we want to add a 1 to the beginning. We want to add a 1 to the beginning, as in to the least significant digit. But we can't just do +1. We have to bit shift n left by 1 and then add 1. Okay, that actually worked. And then if we throw the exceptions, we get the right answer. And then we can, here, you return a list of string, or you return an index of how much you should skip by. Returns a partition or an amount to skip by if this partition was not a palindrome. Okay. The amount to skip by is I. Yes, it's either I or it's like really close to I. It's like I -1 or something. Because if you have this, and we're considering this split, and then right here we've decided this doesn't work. Without even looking at the right side, we know this left side doesn't work. So now we would want to increment this left side by 1. Which is the same as adding 0, 0, 0, 0, 0, 1 in the place that failed, 0, 0, 0, 0. So this number is I is 1 bit shifted left by I. So return 1 bit shifted left by I. It's not a try-catch, it's a partition. If partition, if type of partition is list, is instance, if is instance partition list, then you append it. else n plus equals partition. Here we change this to be while n is less than this thing, n plus equals 1. While n is less than, you don't put a range when you do less than. Okay, and then one thing, because this is craziness, let's return a tuple that has a partition and an amount to skip by. Returns a partition and an amount to skip by. So this is partition, comma, skip. If it was valid, you skip by 1. If it was invalid, you have no partition. So this would be or none. And you skip by a lot. If partition, you append it. And then unconditionally, you increment by skip. Okay. Start n at 0. Let's submit. Wrong answer. I'm missing CDD. Let's use the test case. And let's add some prints. Print ni substring. We never considered DD. No, it's not binary of I that we care about. It's binary of n that we care about. Why are we only looking at... Oh, yeah, we're only looking at stuff that has a 1 in the last spot because of this stupid trick that I'm playing here. I think I'm already doing this, but do I have to look at 1 extra digit? Yeah, like, here's something I would like to try. Never skip ahead. Just give me every answer. So I'm still giving every answer here. Here I have CDD. this looks like every answer. So if I add this back, why would I be missing CDD if it's included, or C comma DD? If it's included here, why am I rejecting it when I add this? Because these are both palindromes. C, D, D. Like, I'm considering DD. I guess print not a palindrome, and then the thing you think is not a palindrome. Oh, I must just be not skipping the correct amount. One of the things I was wondering is, should this be n minus 1 or I minus 1, so that we're... Or actually, should it be... The reason I think it might be minus 1 is because we added an extra digit. We added a fake digit to n. Like, we shifted this to the left. It's so hard to think about the bit shifty stuff. And I'm taking so long on this medium question. I probably don't need this optimization, but it's so cool. Okay, so the number is 1 less than the number of bits in n is 1 less than the number of characters in the string. Because it represents whether there's a split between any two subsequent characters. So it looks like this. 0 means split here, or don't split here. 0 means don't split here. 1 means do split here. Then I'm adding an extra 1 here to say also always split on the end here, so that I don't have to have an extra case. I kind of think minus 1 is right. And I just need to say if I is greater than 0, else just skip by 1. That works. Let's submit that. No, we're slow? After all that, we're slow? That's so crazy, because we're doing it so optimally. I would have thought. We're skipping ahead a bunch. We're trying everything we have to. There is some redundancy. We're rechecking if stuff is a substring more than we would if we did this recursively. Yeah, we are rechecking if stuff is a substring more than if we did this recursively. All right, well, I'm guessing when I look at the solutions, I'm going to see a bunch of recursive solutions. That are basically checking, like, do I put a split here, yes or no? Like recurse on yes and recurse on no, and backtrack whenever we've already found that something's not a palindrome. That's probably what we're going to see. Recursion. Yeah, that is what we're seeing. Okay. Yeah, that's really a lot simpler than what I'm doing. I wonder if anyone is doing this bit manipulation stuff. Bit masking. The C++ people are doing it. I want to see. There's no Python bit masking solutions, so we're gonna see. We're gonna get to be the first one with this wacky ass way of doing it. All right, on to the next problem. Start the timer. Number 132, palindrome partitioning 2. Given a string S, partition S such that every substring of the partition is a palindrome. Return the minimum cuts needed for a palindrome partitioning of S. Partition S such that every substring of the partition is a palindrome. So that's the same as last time. But instead of returning all of them, it's saying return the one with the minimum number of, of splits, I was calling them. Okay, so first few obvious ideas. Let's get some of the bad ideas out of the way. You can try every way of cutting it 0 times, and then try every way of cutting it 1 time, and then try every way of cutting it 2 times, etc., until you get the answer. Some other ideas. I wonder if there's something along the lines of iterating over the string from left to right, whenever you've found that what you have so far is a palindrome, you remember that you could have put a split there, but you keep going and you try to find the biggest split you can make. Then once you get to the end of the string, if the whole string is a palindrome, you're done. If not, then you go backwards to the biggest split you could have made. And you recurse. You recurse on the right side of the string. I guess the problem is I'm thinking like, is it possible that there's a string with a really big palindrome on the left and then a bunch of tiny palindromes on the right, but there would have been a better one if you had accepted one of the not biggest splits. I guess the question is, can you do this with a greedy algorithm? If you always try to take the biggest split, does that always give the right answer? I think we'll have to think about how palindromes work. It's hard to come up with examples for this. I'm thinking like A, B, A, B, A, B, A, B, A, B, A, B, A, C, maybe C, A, 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 C, A, 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 C, A, B, C, D, E, F. A, B, C, D, C, B, A. I mean, you'd have to have the split not. So let's do B, 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 B. It's so hard to imagine an example like the one above where those are two possible splits. Because this is a palindrome, this is a palindrome, and then all of these split separately are palindromes. A better one would be this is a palindrome and this is a palindrome. But that's the greedy one. That's the one where you took the biggest one you could. I'm trying to think of an example where taking the biggest on the left side leads to not the best answer. There's B's here. I just can't. I don't know how it would not lead to the biggest answer. to the best answer. Let's think of this for another minute, because I don't have a reason why it would lead to the best answer. I just have trouble thinking of a counterexample. All right, greedily take biggest left palindrome, then recurse. That's an option, but I can't prove that it'll give the right answer. I can't prove it in my head. Other options would be a tree traversal through the recursive tree, where you try where you go through them in the order where you're going to find the shorter answers first. So you you check if the whole thing is a palindrome first, obviously, and then now you have to do one split. You try every location of split. And then for each one, you recurse on the left side and the right side. And you do it in a depth first search. So depth first search, recursive. That'll also work. And I'm going to try that because I think that will give the right answer. I can see how that will give the right answer. And it's hard to see how you could do it faster than that unless there's a... Yeah, even if the greedy algorithm works, it seems like they would be about the same speed. Okay, let's try the depth first thing. So from collections import DQ. That's Python's version of a queue. Queue is deq that starts with s, our full string. While there's still stuff to explore in the queue, pop q.pop left, because it's depth first. This is our substring, I guess I'll call it. If substring equals itself backwards, then that's the answer. The thing is, the queue needs to save more than just the string. It also needs to save... Yeah, this... I got confused. I'm not even doing it recursively right now. I'm trying to do a real depth first search. I'm unrolling the recursion to make it depth first. So I guess here I'm not storing a string, I'm storing a partition. So when you pop left, you pop a partition. So then what you're doing is for substring in partition, we're going to try partitioning it. If substring is not equal to, or why don't we try first? No, maybe we should. Okay. No, we can do that later. Let's just add is solution partition, which is a list of strings. Cool. Return all substring equals substring backwards for s in partition. Now, for each substring, we'll try splitting it at each position. So for I in range length of substring -1, S1 equals substring starting at I, S2 equals substring, or sorry, not starting, well, yeah, well, up to I and then starting at I. This feels like it's not, like the greedy solution is going to be the right answer, and this is going to be, it's going to be correct, but it's going to be really slow, I think. But let's see this through. So for every possible split, we add that to the queue. So queue.append basically partition and S1 and S2. The order doesn't matter. Let's just call this new partition. This needs to be partitioned, but without substring. So let's do new partition equals partition.copy, new partition.remove substring, new partition plus equals S1 and S2. And then if is solution new partition, just return it. Although then the order is going to matter, I think. And if you get through everything, then return an empty list. Oh no, network error. That's not good. Let's try refreshing. I'm not logged in. Okay, luckily we didn't lose anything. Time limit exceeded, probably because I'm splitting. Actually, I'm not sure why. Let's print the queue as we go. No, that's obviously not going to work because we're still going to exceed time limit. Oh, output limit, good. Okay, I think we need the I+1s here. Oh. It just wants to return a number. I didn't realize that. Okay, well this is definitely not the way to do it then. Number of cuts, so it's -1 here. I think this is going to be way too slow. Let's see though. Oh. If is solution S, return 0. What? Oh, wait, not S, but a list that... list of S, or like... Sure. Oh, I guess that's okay, but why don't we call this P? I don't know why that's not working, but let's just do it the stupid way. If S equals S backwards, return 0. Submit that. Prediction again, this will be too slow. Memory limit. Okay, then I'm interested in thinking about the greedy algorithm more. Is there a reason that I can think of why consuming the most you can on the left necessarily would be part of the solution? I don't know how to prove it. It just seems like yes. It just seems like you can't. There's nothing I can add here that would make me want to take something less than the most I can here. I just really can't think of a way that that would make sense. Okay, here's something else actually. Well, I was gonna say memory limit exceeded. We don't actually need to hold on to the pieces of the solution that are already palindromes. That would save a bit of memory, but the real problem here is the size of the queue, the length of the queue, not so much how big each thing in the queue is. Okay, let's spend a few minutes just trying to make this a little better, and then we'll switch to the greedy. So I don't actually need I don't have to hold on to the pieces that I've consumed. So if instead I keep a count of how much I've consumed, and I just return that, so each thing in the queue would be oh, you know what? The other the other thing is I only have to split when the left side of when one of the sides of the split is a palindrome. There's never a reason to split otherwise. So So I can actually just store the part that's not a palindrome yet, so S, plus the amount of cuts we've needed to do so far. So this would be not palindrome, comma, cuts. You return cuts plus 1 here. We were not going to need is solution. So we don't have a for substring. We only have the not palindrome. So let's just call that substring. For each place that you could cut, you try both sides. If one of the sides is a palindrome, then you append the other side. So let's just delete this. If S1, do I care about if one of the sides, or do I just care about if the left side? I could just care about the left side. Let's just care about the left side. Well, I still need the right side to be appended. So if S1 equals S1 backwards, then Q dot append S2 depth plus 1, or cuts plus 1. If S2 equals S2 backwards also, then just return cuts plus 1. Okay, cool. We got over the hump of space exceeded. Now it's just the time exceeded. So we could try to do the, well, I'm just curious to see what does our search space look like as we go. This is Okay, yeah, I guess we run out of all of the 2 cuts, 3 cuts, 4 cuts, 5 cuts. So it is doing what I want it to do. Interesting. It's hard to make this depth first search version prioritize any order. The order is only going to matter within the depth because we're still going to do everything of a certain depth before we consider anything of the depth one higher. Okay, then the last thing, or then the next thing we can try is the greedy. The greedy approach, and if that doesn't work, we'll at least get a counterexample in our test cases. So for I in range len of s, if s up to I is equal to s up to I backwards, then s cuts equals 0. And then I want to go backwards. I want, give me the biggest one. Give me the biggest palindrome you can first. Then s, replace it with s up to I. And try again. While cuts or all true. If not s, return cuts. -1. This is such a weird way to do it because we're going to increment cuts when we go down by 1. Here, we can just start cuts at -1. So if we've cut everything out, then we return that. Geez, what am I doing? For decreasing sizes of cuts, if that cut causes the first part to be a palindrome, then slice it off and try again on the right side and increase cuts by 1. Cuts plus equals 1, break. And then if it never happens, we'll return 0 or something. No, there's always a way to make a palindrome. You could split every character up and that would make it a palindrome. This is so weird looking. Does this make any sense? Let's print to see what's going on. We keep trying more and more cuts. For some reason, S never gets consumed all the way. Just to check, Python ABC or ABC, if I slice that at 0, then I get ABC again, but I'm gonna start with 2, or actually I'm gonna start with 3. Oh, this needs to be -1, so that I start with 2. So I want it, no, I do actually want it to not be -1. I want to check if this is a palindrome. That's not a palindrome, so then we check if this is a palindrome. That's not a palindrome, so then we check if this is a palindrome. That is a palindrome. So now we set A equal to this. Why isn't this working? Like, there's a lot wrong here. The first thing that's wrong is we should have split at AA, not at A. Print splitting at I. S up to I, S after I. Okay, so we did. So now S is B, which is right. Then we should split after B. We should be splitting after B. Why are we splitting at 0? Shouldn't 1 have worked? Yeah, why are we starting at 0? Oh, because you need a +1 when you're doing range if you want it to include the top end. Okay. So is this right, or is there a counterexample that we couldn't think of? Aha! This is the counterexample we couldn't think of. This is one where the greedy answer means you need 2 splits here, but the not greedy answer but one of not greedy, but not consuming the biggest thing you could is the best way to do it. Huh. Okay, then the next thing is, I think you're always gonna you always want to consume either as much as you can on the left or as much as you can on the right. So if we went back to our depth first search idea, instead of finding every split, we could just find 2 splits each time. The largest on the left and the largest on the right. So once we find one of these, we break for j in the same thing but reversed. Let's just copy this. Reversed range. If j is greater than I, basically, if we find if we start going over stuff we've already seen, so if j is less than or equal to I, then break. Otherwise, do all the same stuff. This time, S2 is the one we care about. If S1 is also a palindrome, then you are done. Otherwise, you recurse here. Memory limit. How did we go back to memory limit? I think we need to go back to printing the queue. This is really hard to read. I want to look at one of the less weird test cases and make sure I'm still giving the right answers there. I am. And what about for this test case? I do give the right answer, so I'm gonna have to look at the really confusing test case and try to understand how I went back to print to oh, actually this is even better. A test case where I get the wrong answer. That's a simple test case. Oh, does that mean there's a way to do it where you don't want the biggest palindrome, either the left side or the right side biggest palindrome? So we can see that we would want, well, it said the best answer is 3. So is that BCB ABABA 1, 2, 3? Yeah, this one you need to take neither the biggest left palindrome nor the biggest right palindrome. because that would lead you to take CBC, which would be wrong. That's not part of any optimal answer. Actually, yes, it is, because you've got split here, split here. So 1, 2, 3. So this is the one where you're greedy from right to left. Okay, so why am I not finding that in my search? So the first split should happen at j equals 0, 1, 2, 3, 4, 5, 6. The other thing I can do is this, which is j plus 1, so that or I plus 1 is what I mean here, so that I know that I'm not retracing over the i's. Obviously, this is not an argument to reverse, it's an argument to range. I want to just print every substring cuts j s1 s2. Oh, I'm not doing this properly. I would actually want to iterate from left to right. How do I say this? I want to iterate from left to right and take the right side. So don't iterate reversed. You can still start at I. J, is this just it? I think this might just be it. Yeah. Okay. And does it work? Or is there another counterexample where you want neither the left nor the right? Greedy. Expected 1. This should be the left greedy answer. And actually, this should not start at I plus 1. It should start at I. But why doesn't this test case work? This should be the left greedy answer. So print me out the queue. Oh, yes. Okay. It's because the left greedy answer needs to go reversed. So we want to start with the biggest substring. Then once we find that, we stop. Then we want the other way around. So the other way around should start at 0 and go to I. Submit. Left and right greedy, is that the right way to do it? Okay, probably a counterexample to the left and right greedy theory. So one, 2, 3, 4. How do you get 3? I'm still looking for that. One, 2, 3, 4. No. 1, 2, 3. Okay, let me copy this. So the left greedy would give you this. Then let's start with what's the right answer. The right answer for this is 1, 2, 3. Three splits. This one you can get from the left greedy. This you can't get from the left greedy. This you can get from the right greedy. And this you can get from the right greedy. So my left-right greedy thing should find the answer. Which means we have just a regular bug, not that our concept is wrong necessarily yet. Oh, I plus 1, because we want to consider the case where you get all the way to where you're looking at the substring, the same substring that the left greedy found. So why do I think you stop at I plus 1? It's because I don't want duplicates. And would I get a duplicate? No, actually, I wouldn't. So I think I just need to go all the way to len of substring minus 1. I wouldn't get a duplicate because I'm not checking the same side of the string. The only time I would get a duplicate is when both S1 and S2 are palindromes, but at that point I just I return the answer. So that never happened. That never gets added as a duplicate to my queue. Okay. This is a problem because this is just saying our whole strategy is not going to work. This is just one of the big ones. So the left and right greedy depth first search is going to take too long. That's a problem. Because at each step I only branch twice. At most twice. I only branch the most between. This gives you a palindrome and and 2. So I branch at most twice, and then okay. I just had another idea that's going to be really disappointing if this is the way to do it. And the other idea is to do it recursively. So if the length of S is 1, that's our base case. You need 0 cuts for that. From func tools import cache. I'm gonna add a cache on this. If otherwise you find the splits where you can. So for I in range len of S, the answer is we take the minimum of all of these. So candidates equals empty list. Candidate equals, or like S1 equals S from I. S2 equals S. This is S from I, this is S up to I. Do you do +1? I'm trying to remember. You do +1. If S2 is, or S1 is itself backwards, then this is a candidate. So candidates.append we recurse self.mincut of S2. The other base case is if S is itself backwards. And then you just return the minimum of candidates. Of 1 plus candidates, because you had to take a split. Oh no. It's really that simple. I mean, we're still far from having a good time. I've been having a good time, but we are not having a good time. I wonder if this is just about the order that we're checking in. No. I kind of want to combine both ways of doing it, because this is not going how do I say this? This is not doing a depth first search. This is doing, or sorry, this is doing a depth first search. It's not doing a breadth first search. I think I've been saying that backwards this whole time, because I meant a search from depth to depth when I was saying depth first search, which is not what that means. Yeah, this is not a depth first search. This is a breadth first search. But I can't do a breadth first search if I want to be able to cache the substrings. Like, this is stupid, but a lot of time is going to be spent doing recursive calls on really simple cases. So if len of s equals 2, we can just say you need one cut for that. We don't have to go through the process of trying the splits and finding a minimum. But no, that's not it. There's a real thing you can do to speed this way up. I'm going to think about this very briefly before going on to the answers, because I've already spent so long on this problem. We're not doing well today on these problems. The idea with the depth first search is that you have to go all the way to the depth to find all the way to the leaf nodes to find the answers that start being cached. I would have thought that adding a reversed here should help, because then we're searching through the big palindromes first. I wish I could see like which problems were slow. Yeah, adding the reversed barely changes anything. This isn't going to change much, but I don't actually need to remember the candidates. I can just remember the minimum. From math import infinity, minimum equals min of minimum and this new thing. And then return 1 plus that. Oh yeah. Return 1 plus minimum. That's not going to save any time. That's just, I mean, it's going to save an imperceptible amount of time because we don't have to iterate over the list of candidates. So I like, this isn't going to work, but I had an idea in a previous problem of doing something like a bounded depth first search, where you have some limit to how deep you're willing to go, and then you give up after that limit, and then we successively increase the limit so that we are not wasting our time down in the depths of a dead end. But that only works if the true solution has a pretty low depth. I don't see any obvious ways that I can shortcut. Because I'm already cutting off, the left side already needs to be a palindrome. What else could I shortcut? The right side doesn't have to be a palindrome. I guess we could do this thing with a best depth equals infinity, where once we've found a solution, the thing is we'd have to remember the depths, and then that screws with the caching, unless we did our own manual caching, which didn't take the depth into account. So basically what I'm thinking is, once we've already found a good solution, we don't need to keep looking for solutions that are deeper than that. The problem is that only works if we find a good solution early. We might start by getting lost in the depths of a dead end and then find the good solution at the end. So this helps, but not necessarily. Let's try it. I don't think it'll help very much, but it'll be interesting. So our cache is a dictionary from string to int. An interesting thing about the cache is that it can actually be int to int, because this is always the right side of a string. No, it's not. Yes, it is. That's kind of interesting, actually. It's always the right side of a string. So let's keep this really simple answer. And then let's make this more complicated thing where we've got our manual cache and we've got our shortcutting. Cache is a dictionary from int to int. When you call mincut, it just calls our own mincut. With 0 as the 0, 0. 0 as the, what am I trying to say? 0. Zero as the first index of the substring, and then 0 as the depth. And then let's define our own mincut that takes I as an int and depth as an int and returns an int. It does some stuff and then we return that. Okay, and the stuff it does is this. So you're not checking S, you're checking S starting at I. Everywhere where we're doing S, we replace it with S starting at I. We don't need this. Let's call this J instead of I. And these are S starting at I, S starting at I. You don't do mincut of S2, you do mincut of J. You're not iterating over S. You're iterating over S starting at I. So we're slicing it and then slicing it again. The other way to, well, that's fine. And then this is I plus J. So I think this will give the same answer. Which one does it think is, it thinks S is a int object? Oh, because I need to be calling my own mincut here. Depth plus 1. And I'm missing a plus 1 here. The J should always be plus 1. Okay, it gives the same answer. So let's start by just adding a cache here. No. Let's do it all. Let's do it all. We have our own cache. Now let's start simple. At cache and no depth. So this is exactly the same as before, but we're not storing a bunch of strings, we're storing a bunch of ints. It doesn't help, as expected. Okay. Now let's do the depth thing with a manual cache. So the cache only cares about I. Cache, non-local cache. Cache of I equals 0. cache of I equals mincut return cache of I. Wait. Something's wrong here, because then you would do this in linear time, because you're only ever checking each I. Hold on. Let's go back to... How is this not linear time? Without the depth. I don't even want the depth. Wait. Go back. Get rid of depth. Add cache. If the only parameter is one integer and the integer only goes up to the length of the string, then this should be linear time. How can it be taking so long? Print I. Show me one of the slow ones. It's not going to. Okay, well then let's just unroll it into a dynamic program. And just compute all of the I's one by one. So cache equals it's a list of ints as big as len of s or one smaller than len of s, actually, because there could be one less split as there are no, it's as I don't know, but I don't think this matters. So cache is this. Return or cache of I equals 0. Cache of I equals 0. What am I trying to say here? I'm trying to unroll this into a recursive thing. So instead of having a recursive function, I'm just going to do for I in range len of s don't return stuff. Just give me the value, or set the value of cache of that to be what it is. So don't return, just set the value. Here you're just going to return cache of 0. Here you're going to return, you're not going to return, you're going to set cache of I to be this. Here you're not going to recurse, you're just going to get the value of cache of this thing. And since we're going from 0 up, which would mean doing reversed, so we always have the bigger ones when we do the smaller ones. My cache size might be 1 too small. Wrong answer on everything. Do you just return, do you remove the 1 at the end? Submit that. This can't be slow, it's linear. It's slow. You just have one for loop. I guess it's n squared, but you have one for loop for each letter, and then another for loop for each remaining letter. So it is n squared. Okay, I look forward to seeing how other people did this. ON space. This, I need an explanation. This is like, it has an explanation, but it's written in such a messy way. I need a better explanation. N squared, that's what I had. But why was I so slow? No explanation either. So they're doing dynamic programming. They're doing for I in range 2 times n, L and R are the left and the right side of the I don't know. I think this is doing what we're doing, but in a really confusing way. I think they're checking if stuff is a palindrome a lot faster. I think I'm actually doing that very slowly. Because so this is n, and then I've hidden it that this is also n. So maybe you could go faster by recognizing palindromes faster. Yeah, I actually think that's it. If you recognize the palindrome faster, this would truly be n squared instead of my kind of n cubed thing here. So to recognize them faster, instead of checking the whole string each time, every time I add one character to the end of S1, I should only have to check O1 new things if I remember why the last string wasn't a palindrome. So that's how you would turn this n cubed into n squared. This is actually n cubed. O of n cubed could be made O of n squared by checking if S1 is a palindrome faster by remembering intermediate results. Okay, I'm happy with that. Let's move on to the next one. And let's do this one fast and correctly. Start the timer. 133, clone graph, medium. Given a reference of a node in a connected undirected graph, return a deep copy, clone, of the graph. Each node in the graph contains a value int and a list node of its neighbors. Because it's undirected, is there redundancy? Do both sides of the relationship have a reference to the other? For simplicity, each node's value is the same as the node's index, one indexed. For example, the first node with val equals 1, the second node with val equals 2, and so on. The graph is represented in the test case using an adjacency list. An adjacency list is a collection of unordered lists used to represent a finite graph. Each list describes the set of neighbors of a node in the graph. The given node will always be the first node with val equals 1. You must return the copy of the given node as a reference to the cloned graph. So you're given this with 1. If you have new nodes with all the same values, it's correct. If you try returning 1 itself, it's wrong. If you have the same nodes with different values, it's wrong. Okay. The only thing I'm still confused about is whether I have a reference on both sides. I guess I can just find out. Print node and node dot neighbors. and spell it properly. Spell it the American way. Print does this work? No. Can I print hash of a node? I just want the a unique identifier of it. Okay. And then print print hash of neighbor for neighbor in node.neighbors. But I actually don't want that. I want let me just, if node and node.neighbors without an O, print node.neighbors 0 and node.neighbors 0.neighbors. I just want to know if I get back to myself or not. It says it's undirected, which is why I think I might. It's just that I might not be node number 1 in the neighbors list, or I might not be the first one. So I am the one that ends with E10-0. And I am back in this list. Okay, so both sides have a reference to the neighbors, to their neighbors. They have a reference to each other. Okay, now that I understand the format, I can start on the problem. I just want to do a graph traversal, then copy everything. Yeah, that's really it. So def traverse node or none. For n in node.neighbors, traverse n if we haven't visited it. Visited equals set that starts with our first node. And we're going to traverse our first node. We also need if not node, then you don't need to do anything. Otherwise, add it to our visited, traverse it and add it to our visited list. Visited.add n, traverse n. And what do we actually want to be doing with these nodes? I guess collecting them in visited is enough. Then we're going to have all of them. Then we can just do like for n in visited, make a copy. And let's have a root. And we'll return the root. If n here, so then we'll make a node. So copy equals node that has the same val, so n, or val equals n dot val, and has the same neighbors. Though that's hard to do until we have all of the copies. So let's first make our copies. Copies equals this. Copies dot append this. And then for and then let's make it a map that maps from int to node, so that we can quickly grab the node by its value. So it's not dot append, it's copy at n dot val equals node. And then for copy in copies, we'll populate their here's where we do root equals none. We'll populate their neighbors. So copy dot neighbors equals well, this is where we need to know the original one also to see what its neighbors were. So neighbors equals a dictionary from node, or even val. But we can do the same thing here actually. So this will be a tuple from a list of int that has neighbors and node. Let's do node first and then neighbors. So so what are its neighbors? Here we would just do neighbor dot val for neighbor in n. Then copy neighbor values. Copy dot neighbors equals copies of neighbor value. We'll do this, iterate over these for neighbor value in neighbor values. Copy dot neighbors dot append. Copies neighbor values. And then finally, if copy dot val equals node, our original node dot val, then this is our root. And then we return it at the end. It's a dictionary from int to tuple to list. Yes, I have one missing. Maximum recursion depth. Yes, because I forgot to check if n not in visited, then you do these things. We don't want to otherwise we get stuck in a loop where we're visiting the same node over and over again. Node object is not iterable, yes, because this needs to be dot neighbors. Cannot unpack non-iterable, yes, because these are the values that I want to iterate over, not the keys. And then you have to call that. Unhashable type list. Where? Where am I trying to hash a list? I don't think I'm trying to hash a list. Oh. This is also not what I want. Here I want the node itself. I don't know if that is the issue. Visited is not supposed to have any nones. Oh. No, how is it ending up with a none? Oh, if we don't even have, oh, okay. If not node return none. Okay, submit. All right, easy peasy. Yeah, let's take a look in case there's like a really clean way to do it that I didn't think of. No. It's about the same. It looks like they managed to construct the copy during the traversal. Yeah. They just add both sides. They add it to both sides of the copy while they're going through instead of doing that at the end. But okay. Next problem. And this time we're going to solve it quickly and optimally, and we're going to have fun, and it's going to be great. Number 134, gas station, medium. There are n gas stations along a circular route, where the amount of gas at the ith station is gas of I. You have a car with an unlimited gas tank, and it costs cost of I of gas to travel from the ith station to its next I plus 1th station. You begin the journey with an empty tank at one of the gas stations. Okay, so we have costs and we have gas. Given two integer arrays, gas and cost, return the starting gas station's index if you can travel around the circuit once in clockwise direction. Otherwise, return -1. If there exists a solution, it is guaranteed to be unique. Okay, I don't know why it would be guaranteed to be unique unless they're just gonna not give me a solution, inputs that are not guaranteeing a unique solution. So, I mean, it's basically just try. Okay, well, here is O(n squared). Try every starting point, right? and then for each one you go around the circuit. We can probably do it linearly by going around just once, and then at the end of that we should have enough information to know where the starting point that works would be. So I just want to write down the bad answer first, just to get it out of the way, because I think it's going to be really simple. So for I in range len of gas, they're both the same length. Current gas, you start with, let's say you start with 0. Then for J in range len of gas, so you go around the circle. J or current, you subtract the cost that it took and you add the gas that it took. To get to the next one, if you are ever negative, negative or probably 0. Why don't we call this tank? So our tank starts at 0. Then we refuel where we are. Then we use up the gas from where its cost is from I to I plus 1. Okay, yeah. If the tank is negative at that point, then this I is not going to work. Which is annoying because I want to break out of this and then continue out of this. If tank is greater or equal to 0 at the end of this point, then you have your answer, return I. So this will give the right answer, but we're going around and around and around for no reason. This one's supposed to be impossible, but I said it was possible. So you start at, let's say you start here. Then I say you refuel and then you travel to 3. That should give you -1 gas at the end. So you should break and not find that as the solution. Oh, I forgot we have to go around. So this needs to be mod len of gas, mod len of gas. You're not just going to the end, you're going all the way around. So I should fail right away here. Let's just confirm that I am. Tank is empty. IJ. Okay, the one that it's getting confused on is 4. Oh. I forgot to add j here. I plus j, because we're starting at I and then we're going around j. I was just staying at the start the whole time. All right, so I said tank is empty, tank is empty. Okay, so then you're supposed to return -1 if you never found anything. If you never found a solution. All right, so this will work. We can do better. I'm not even going to submit it. So the reason we should be able to do better is the whole thing is symmetrical circularly. So once I've figured out the amounts of gases, how do I say this? Once I've figured out what your tank will be left on at each stop in one journey, the answer for the next journey is the same, but just offset by, or like the values of all of the tanks are the same, but offset by a different starting amount. What am I trying to say? I mean, like, I mean, here we started at 0. Once we're doing a different solution, we're going to do the same stuff here, but we're just going to be starting at, like, not starting at, but our tank will have an amount that's non-zero. And I just have to know if there's any starting point where you would have enough gas. So let's say instead of starting at 0, I started at n, like I had n amount of gas. Like, we're not doing a loop, an outer loop. We're saying the amount we start with is not determined, it's n. Then then if you ever go negative, you can't, then this was not the right solution. We're trying to think, is it ever possible? So instead of looking at what would not work, what we want is I'm having trouble getting the last step of this idea, but it's like it's something like, don't think of the tank as having an actual amount of gas in it. Think of it as having a indeterminate amount of gas. And then we're trying to find what's the amount of gas where this would be possible, and then check if any of the starting points gives you that amount of gas. How do I... How do I do this? It's so the... I think the trip that uses the most gas should come last so that you've accumulated... No, that's not necessarily true, because you could have like, let's say 1, 1, 1, 1, 1, 1, 1. 1, 1, 1, 1, 1, 1, 1, 1. And then this one uses 2. And this one gives 2. So this is, or let's do it the other way around. So this is gas. This is cost. Okay, this is helping me visualize it. So, and then you subtract cost from gas. So you get 0, 0, 0, 0, 1, negative 1, 1, 1, 1, 1. No. These you subtract. These are 0, 0, 0. So once you've subtracted everything, that tells you the amount that you'll gain or lose at that stop. Or like between those two things. Then if you sum this up, and it's negative, that would mean overall, that would mean you can't do it, but it doesn't necessarily need to be negative, because let's say this, well, actually, maybe it does necessarily need to be negative, because let's say this costs 9, then this is negative 8. This one's negative 8. This is not possible. And you can tell that because this sums to a negative number. If it were possible, we'd have to pick up enough gas to get past this point before getting to this point. The confusing thing is, let's say we do put a 9 here. So there's an 8 here. Here you can make the trip from anywhere. But in the examples it's going to give me, there's only one place where you can make the trip from. So what's an example where there's only one place you can make the trip from? Let's use their example. And then let's look at the net that you get from here. So subtract this from this, it's -2. Subtract this from this, it's -2. Subtract this from this, it's -2. Here it's 3. Here it's 3. So this sums to 0. Which means, I think it means it should be possible. Where would it be possible from? Well, it could be possible from, it should be possible from the first non-negative difference here. I mean, it's possible in the position where you start by gaining the most gas. Is there another example? No. The only thing I'm not sure about is, let's say there's 2 dips. How do you know which one you need to fuel up for first? It's something like you start in the place where your net gets you the largest amount. And then it's also circular, so you have to remember to loop back around. So oh my god, I'm having so much trouble on this one that I didn't think should be this hard. Like, I can see that we need to start here, otherwise we'll run out of gas. I'm just trying to think of what the rule is specifically. It's something like you start where you can pick up the most gas. How do I say that in a objective way? You start wherever the sum of subsequent stops is greater, or has the highest peak. And so obviously one way to do that is to try every starting position, sum their things one at a time, keep track of which one has the highest peak. That's not going to work because that's n squared. How can we figure out which one's going to have the highest peak? By going through only once or twice. Because I guess if the answer was you start after the lowest valley, in other words, you save the difficult part for last, then we could figure that out by going through only once. But I don't know if that's necessarily true. I think the main thing is you bank up yeah, the main thing is you bank up the gas, not you avoid the hole. Because in this case, they're right next to each other. But if there were like a bunch of zeros in between, the place you would want to start would be, I guess if there were zeros in between, there would be more than one solution. Because you could start anywhere between this and this. Okay, then if we know there's only one solution, I think the answer is you start after the biggest valley. So then you do a second order thing here, a list of one shorter, where you say the difference between these is 0, 0, 5, 3, or 0 actually. And then you pick this spot to start in. Or no, it's not one shorter because you also go around, so it's -5 here. So if we did it the other way, it would be the difference between me and my previous element, and then you pick whatever is the max here. Okay. Net equals empty list for j in range, net dot append this minus this. Say for I in range, get rid of the plus j. And go more than one so that you loop back around. No, that's I think that's already handled actually. Print me net so I know that I'm on the right track so far. Yep. Now give me the differences. So this is like the derivative. Yep, that's what I was looking for. And then whatever is the max. Whatever's the max is what I want. And I think if the sum is less than 0, then the answer is -1. Or I guess you could just find the max and then try from there. And if you can't do it from there, then you can't do it. So for I in range whatever, we can change this after to do this all in one loop. Best equals -infinity from math import inf. Oops. Best equals max of best and diffs of I. Best I is 0. Best I is I. Return best I. That's gonna give the right answer when there is one. Or -1, I guess. But it's also going to give it an answer when there isn't one. So now we have to I wonder if there's a heuristic or if we just need to try traveling from there and see what it does. It's like if sum of net is less than 0, return -1. Does that work? I thought there would be a counterexample. So here, our net is this. Our diffs are this. I didn't know that there would be a counterexample to this. I thought there would be a counterexample to my -1 heuristic. I'm saying you should start here. Oh, -1 mod len of gas. Though I guess I'd rather it just be best I. And we just change this to be I plus 1 on this side and I on this side. Why do I have to do the minus 1? I don't actually get that. Let's come back to that. But it doesn't work with this test case. But it would have worked if I didn't do the minus 1. I guess I don't understand why I'm doing minus 1. So let's try to understand that now. Because I think the best place to start here would be 0, 1, 2, 3. But I'm outputting 4. Oh, because I'm just always outputting the last thing. What I want is if best, if diffs of I is greater than best, then best equals diffs of I and best I equals I. Submit that. Okay. Is this a counterexample to my heuristic? No, because it didn't expect -1. I'm just not returning the right place. It's a counterexample to the start where there's the biggest difference between losing and gaining, which now that I think of it, yeah, that's not what I was looking for. I was looking for the place where there's the biggest gain on the way. So this isn't even what I meant to do. How can I tell that there's the biggest gain on the way? What I want to know. That the thing I want, and this is also the property that would let you have enough gas, is that starting here, starting wherever, the sum from here and cycling back around never goes negative. Like that's what I want. That's what I actually want. And then I'm just trying to figure out a way to tell that. And it's something like you take the cumulative sum from here but it's not quite that, because that doesn't tell you if it ever goes negative. Oh, I'm having so much trouble when I shouldn't. So the thing I'm picturing now is I have this circular array. Like, this is really the thing I care about. I don't care about gas and cost. I care about this. And I care about whether this ever gets to 0 when you're summing it starting from somewhere. The sum starting from anywhere is the same. The full sum starting from anywhere is the same. The graph of how the sum is going changes depending on where you start. The circular graph it changes, but it's always offsetting by the graph of where, this is hard, I need to draw this. So you've got some graph that's like you gain gas, you lose gas, you gain gas, you lose gas, you gain gas, you lose gas, you gain gas, you lose gas. Then if I were to start at a different position, the graph would be the same, but this part would be cut off, and this part would replace it, or it would be like offset to a side. And then this part would come back over here. So cover these. This is the thing I'm having so much trouble with. So what am I drawing? I'm drawing like the value of the sum going all the way around from any starting point. It's the same graph just offset. Here, this is a better way to. Right. So it has the same peaks and valleys. I think it also can be shifted up and down. I just need to think about this for a second. This is the thing we care about. I'm having trouble picturing this, but the circular graph of the way around I'm just having so much trouble picturing the thing that I'm trying to think of because it gets offset in ways that are hard for me to picture. If I go back to the idea of I want to grab the most gas earliest, I'm just losing focus. I'm having trouble concentrating. I will do this. I will succeed. You've got a circular array. You're trying to find the point in this array where the sum of the subsequent elements will never become negative. The graph of the sum of the subsequent elements has the same shape for each starting position. I think I need to write this down. Graph of the sum of the subsequent elements has the same shape for each starting position. The graph of the sum of the subsequent elements has the same shape for each starting position. Which means we can find its minimum for one graph, and we know for one starting position, and we know where it will be for other starting positions. So that's thing number one, that's thing number two. The thing number three is it has the same shape, but it's offset vertically depending on where you start. The graph is offset vertically depending on where you start. Wherever you start aligns the graph at tank of 0. Okay. So if we can find the minimum amount of gas that you will have in O1, we don't need to go all the way around. We already know where it's going to be. Okay, here's the other thing. The minimum is also going to be where you want to start, because the only way that there's only one solution is if the minimum is going to be negative for all but one of them. The one where it's not negative is going to be the one where you set it to 0 by starting there. Eureka? If you start at the minimum, it can't be less than 0. Okay, so we build our net. We find the minimum, so starting wherever the minimum is from there, it'll be there but offset in all the others. So lowest equals infinity for I in range line of gas. Cumulative sum starts at 0. Cum sum, or we can just call this tank. Tank plus equals net of I. Lowest equals min of tank and net of, or min of lowest at tank. This is all starting to make sense. We don't just want the lowest, we want the position of the lowest. So if tank is less than lowest, lowest equals tank, lowest I equals I. Okay, now that we've found the minimum, that's the answer. Because no matter which way around, you're going to want to start there, because that's going to give you, yeah, that's the answer. Or it's just that you have to start one after the minimum. So mod len of gas. Submit, fingers crossed. Wow, we did it. Okay. we can definitely improve this. So we can do this in one loop. We don't actually need to store net. Bring this up here. We'll have to figure out how to do, well, we can just, we're taking the sum, so tank at the end. Well, yeah. We don't need to build net. We can just, as we go, do tank plus equals this. Does this still work? I don't see how you're doing better than that. I'm not sure how these people ended up getting such low run times. This seems like the fastest you can do it. Let's take a look and see if they just have it. Well, this is more than what we're doing. I don't think they needed to do this. Yeah. Okay, so we did better than that. Give me the code. Give me the code. Same as what we're doing. A little confusing, actually. Oh, yeah. I think it's the same as what we're doing, but with some weird math. The other thing I just realized, we don't need our mods here because we only ever iterate over one time. We don't end up going back and needing to circle. Okay, so that puts us in the pack. That Makes sense. And then this, we could do this without a mod by just doing an if, but it's fine. All right, happy with that. On to the next one. And this one's gonna take less than 20 minutes. I can feel, oh, hard. Oh man, okay. All right, we can do this. Start time. Number 135, candy, hard. There are n children standing in a line. Each child is assigned a rating value given in the integer array ratings. You are giving candies to these children subjected to the following requirements. Each child must have at least one candy. Children with a higher rating get more candies than their neighbors. Return the minimum number of candies you need to have to distribute the candies to the children. Each child must have at least one candy. Children with a higher rating get more candies than their neighbors. Does that just mean their immediate neighbors? 2, 1, 2. Yeah, it does. Ratings 1, 2, 2. You need to have more candy than the person on your left, and it doesn't matter if you have more candy than the person on your right. So you get a 2. You need to have, you have no requirements. You could have any amount of candy and it would satisfy the conditions. So we'll put you at 1, which is the minimum. I think I'm understanding that right. So is it just you give the first child how do you do this? It's like you give the first child one. The first child you can, or actually, do neighbors count? They're not circular. It's not a circular array. No. So the first child, you can always do either 1 or 2. I mean, not necessarily, but let's say you give the first, considering them from left to right, you give the first child a 1. You're going to increase it only if you have to. You go to the next child. If they are greater or equal to the last child, you don't have to increase the last child. If they're less than the last child, then you have to increase the last child. And then you give. All right. Let's just do a really naive solution and see if that even gives the right answer. So you give 1 to everybody, and then you iterate through the list over and over again. Every time there's a violation, you grant a candy. Would that work? Would that necessarily give the optimal? So you give 1 to every child. So you start with candy equals 1 times len of ratings. And then for rating in ratings, for I rating in enumerate ratings, where I is the index, you say if or you know what, just for I in range of len of ratings, if rating of I is greater than ratings of I is greater than ratings of I minus 1, or I plus 1, let's just do them one at a time. If this child's greater than its neighbor on the left, then it needs more candy than the one on the left. Candy of I equals candy of I minus 1 plus 1. If it's greater than the one on the right, it needs more candy than the one on the right. And in both of these cases, you take the minimum between what it already is or you take the maximum between what it already is and what I need to grant to it. Okay. Then if you do this n times, you end up with an answer. You end up with the right answer. For blank in range len of ratings, if I is greater than is less than len of ratings minus 1 and that, and then here it's if I is greater than 0 and this. So if you have a neighbor there, return sum of candy. Okay, I'm guessing this gives the right answer, but it's too slow. And the faster way is going to be some kind of dynamic programming recursive thing. Let's just make it tell us. Tell me that this is too slow. Go ahead. Possibly it doesn't even give the right answer, that this ends up in some kind of local minimum. Okay, too slow. All right, so how can we compute a solution out of a partial solution? So if you have the correct answer with the kids on the left, like whatever that answer is, and now I want to add a new kid. How do I combine these into a new answer? So one way is if this new kid is greater than the candy on the left, I just make this be the number one bigger than that. If this new kid is lesser than the one on the left, then we need to recompute this side with the new constraint that this needs to be bigger. I can't just set this one bigger because then it won't, the rest of it might not be a solution anymore. And I can't just increment everything by 1 because I might not need to do that. But I think I can just pass over the list one time to adjust it. Pass over it from the right. Maybe let's do it the other way so that we can iterate over stuff in an order that makes more sense. So here, if this kid is greater than this kid, you just make this be equal to this plus 1, and you keep this as is. If this is equal to this, you just give this kid a 1. And if this is less than this, then you give this kid a 1. And you have to recalculate this. Okay. Def allocate. We're just going to have I, which is an index into ratings. We're going to cache this sucker by adding from functools import cache. We're going to say the base case. So if I equals len of ratings minus 1, you return 1. Otherwise, wait, is it right to give a number? I guess there's two arguments here. There's starting at I, and there's the thing on the left is greater or not. It's so weird though, because then you might as well be calculating with I minus 1. Let's think this through as you're calculating starting at I. You're calculating starting at I, and you have nothing on the left. And then at the end, we'll return allocate of 0. And so we're going to return this is going to just be a count. Returns an int. That's tough though. Let's not do an int. I think the most optimal way is going to be doing an int, but I don't know how to do that yet. So let's return a list of ints. So we recurse allocate of I plus 1. This is the right side. If ratings of I is greater than the right side of 0, then return, this just needs to be 1 greater, and then you add the right side to it. I prefer this syntax. JavaScript style, where you're unrolling the list. If ratings of I equals, it's the same as the kid on the right, then you can just have this kid have a 1. And if ratings, this is just an else, ratings of I is less than the right side, then we have to recalculate the right side. That's the part of the recursion that I'm not sure how to do. You're going to return 1, comma, and then something different. How can you can't, I don't know how to recalculate the right side. That's not like, I can't just call allocate again and it'll give the same answer. I can't just do it manually because that's going to be slow. I have to still do it in a recursive way, but I don't know how the right answer, how it's, what its relationship is to smaller answers. Because right of 0 needs to be bigger by at least 1. And then I don't know how deeply it's going to propagate inside the rest of the children. So I'm picturing something that's going to be hard to draw, but it's like, if the children are this is, each hash is a candy. If you've got like a tower of children and then like whatever else, then when you increase this, it's going to have a chain effect going up the tower. But it's not gonna do anything beyond that. Like you're gonna add 1 here, 1 here, 1 here, 1 here, 1 here, and then you'll be done. You know that you don't have to do anything on the right side of the tower, because if you did, you would have had to do it already, because the left side's already greater than the right side, and you only care about being greater or lesser. So now I'm thinking we need to do some kind of pre-processing to find the chains. So that we know quickly, if we add to this, it's going to add 1, 2, 3, 4, 5, 6, 7, because there's a chain of like 7 on the left of it. What about the right chains? The chains pointing left. I think we might be figuring those out already by doing this. I think we are. Okay. Okay, then let's start by figuring out the chains. So we only care about the chains that go from left to right. So that's going to be 0 times len of ratings is how it starts. Then 4. Actually, let's just let's start it empty, and then for I in range ratings, if ratings of I is greater than ratings of I plus 1, no, other way around. If the next thing needs to be greater than this thing, then chains.append basically you have to continue the chain. So whatever was on your left, you need to be one bigger than that. Else, chains.append 0. Okay, print chains. Len. It's going to complain about this. Oh. If I is less than len of ratings, I mean just don't iterate that much and then add a 0 at the end. Oh, if the first one, wait, I'm doing this backwards. I want to iterate from right to left because the thing I want is that the value of this here knows about the things on the right. So this is going to be 7, 6, 5, 4, 3, 2, 1. And then there's no chains here, but if let's say there was, then this would be 1 again. No, this would be 1, this would be 0. I want to know every time the thing on the right, yeah, I want to have a chain of things on the right. So I in reversed range, we need to know them from right to left. Let's start this as 0 times len of ratings. Anytime here, chains of I equals chains of I plus 1 plus 1. So you're one more than the one on the right. Okay. You're a higher rating than this. So this is close, but I meant for the 1 to be all the way over here. So do I have to do chains of I minus 1? It's because I is greater than 0, which is why there's a chain. So I Oh, it should be greater than 0. If the rating is greater, then the chain needs to start there. Okay. Here, there's no chain going in that direction. Okay, so we've pre-processed the chains. Now we go back over here. We go back to, we need the, no, we can directly return an int. The right side, this is how many candies we've given out to the right. It's not if you're greater than ratings than right of 0. It's if you're greater than ratings of I plus 1. If my rating is greater than the one on the right, no. If my rating is, yeah. But then I have this backwards, don't I? Because I'm checking the same thing both times. Because this would mean you are greater than the one on the left. So this should be like that. Okay, so let's go back to printing chains because I am confused about that again. You have a higher rating than the one on the right. You have a higher rating than the one on the left. So you have created a chain, yes, from here to here. The chain in the other direction we don't care about. Like we're building that as we go. The chain in the, okay, so I think this is right. Because one of the chains we're just in one direction, we have to remember how many more candies we should have given. In the other direction, we just have to know how many candies to give to this new kid. The other direction, we have to know how many candies we should have distributed across all the kids in order to stay consistent. So if this new kid on the left is greater than the kid to the right of it, that has no implications for the chain on the right, for like the kids on the right. It just means the kid on the left needs one more candy than the kid on the rightmost thing. So the leftmost kid in the chain on the right. So I think I actually have to return a tuple of ints where it returns the candy for the leftmost kid and the total candy for all, and the total candy. So when there's only one, that's the same thing. This is a tuple. In this case, right total, right kid, right total. So I need more than the right kid. Right kid plus 1. That's how much I have. So the thing on the left is the candy for the leftmost kid. Thing on the right is the total, which would be this, the amount for the rightmost kid, plus right total. If they're equal, then you're returning right total plus 1 and 1. So this new kid only gets 1, and the total got increased by 1. If this new kid on the left has a lower rating than the kid on the right, then this new kid gets 1, and we increase the right total by the chain amount. Is this possibly it? Ratings of I plus 1. Oh, I want to return the total. I'm somehow off by 1, but I'm suspicious of that. I'm suspicious that I'm just getting the wrong answer. I don't know why I would be off by 1. All right, let's start by printing the chains for this example that's failing. 1, 2, 3, 2. So the only time something on the right is bigger than something on the left is in the first place. Wait, I think I'm missing a plus 1 here. I think that might be where it was going wrong. Because I forgot to count the one that I'm adding to the kid on the left. So that fixes my plus 1 thing. It doesn't fix the fact that I'm still wrong here. So the chain should only be a 1 here. If I go through this, I'm starting on the right, so 1, I have a 1, and my total is 1. And now I'm looking at this. Ratings of 2 is greater than ratings of, or 2 is greater than 1. So the left kid needs 1 more than the right kid, so this will be a 2. And this will be the total, which will be 3. Okay, then we expand out to here. This is equal to that. 2 is equal to 2, so we're in this case, which means you get a 1 because you're not greater than your neighbor on the right. And the total is whatever it was on the right plus 1. Over here, we've got 3 is greater than 2. So we're in this case. If ratings of I, if 3 is greater than 2, which it is, then the kid on the left gets 1 more than the kid on the right, and the total is that plus the total. And then when we add the 1, 1 is less than 3, so we're in the else. Kid on the left gets a 1. Then we have to increase the kids in the right side by the chain amount, which is 1, because we only have to increase this kid. Oh, we actually don't have to increase this kid because he was already big enough. He was already big enough. So oh, hold on. That's so complicated. They're always going to already be big enough. Because the one on the left is always starting at 1. No, they're not always going to be big enough. It's just if they were a 1, then you have to increase the chain. Okay, so this is elif right kid equals 1. Then you have to do this. Otherwise, they were already big enough. So you can just do 1 right total plus 1. Can we submit that? Okay, what's going on here? So our chains are 2 and then 1. So this kid gets a 1. This kid has a higher rating, so he needs 1 more. So this gets a 2. This kid gets a 2. This kid keeps a 1, so the total's 3. This one's a higher rating, so it goes 3, 2, 1. Higher rating, so it goes the right kid plus 1, and then add that to the total. So 3, 2, 1. Now, this rating is lower than the rating on the right, but the kid on the right already had a 3. Oh, geez, I see. It's not just if they're equal to 1. The chain might eventually overcome Like eventually we might have added enough through the chains that it overcomes and the chain needs to be bigger. No. No, once the chain is broken, it stays broken. Okay, so let's think it through. This 2 is greater than this, or is less than this 3. So we have a chain, but the 3 was already big enough that we didn't need to increase it. So we ended up here. Right kid is not 1. So we ended up here. So we didn't have to add the value of the chain. Then here is the same case. But now we do have to care about the chain. But we're caring about it too much because we're assuming that you had to increase this and this and this, but you only had to increase this and, or like that. The 3 was already big enough. So the chain could overcome. This is really hard to think about. I need to draw this example. So there's the ratings and there's the candy. The ratings was 1, 2, 3, 1, 0. The pre-computed chains are this. No, this is chains. The candy looks like this. You get a 1, you get a 2, you get a 3, you get a 1, and we do not need to increase the chain, though we would have needed to if this 3 were lower. Then you get a 1, and we do have to increase the chain. And now if we imagine that we had another 1 over here, now we might have to increase the chain all the way back to the 3. So it can overcome it. So you're a 1. How do we know whether to add something or not? It depends on stuff's threshold. Like, this guy is at 3 candy, but he needs to be higher than the one on the left. So he needs to go up by 1 if this guy goes up by 1, or if this guy goes up by 2. So what can I actually say about it? It's like, what's the formula for how much this guy goes up by? It's the minimum between 0 and 3 minus like candy of guy at I minus 1. 3 is candy of I. So he is candy of I, and the amount that he needs to go up by this is where it's like when you're increasing something on the left, he needs to go up if this gets to be equal to 3. I just want to encode this in some formula so that I don't have to iterate backwards through and re-increment everything. So I can kind of do it in one pass. We have the chains pre-calculated. It's just that you don't necessarily bring the whole chain up. You only bring it up a certain you only bring a certain amount of it up, but then you might catch the rest of it and need to bring the rest of it up. So there's like a threshold before you need to bring this guy up, and this threshold is 2. So it's 1, 3. So there's a threshold of 2. Where once you run out of, it's like slack. Once you run out of slack, you have to start incrementing this guy. And then once we put a 2 here, once we put a 1 here, this one has no slack. Once we put a 1 here, you have no slack. And we're going to have to increase you by 1, not by your chain amount, but by 1. Yeah, it's like you have slack, you have chain, and then you have slack. And then once you run out of slack, you need to pull the rest of the chain. How do I formalize this? It's like, so the guy on the left is always at 1. And then you have some kind of chain that might have slack in it. I don't know how to store that, but let's say it's a... It's a list of numbers. A list of things like this. This is going to be so simple once it's done, but this idea is confusing. It is like, yeah, it's really hard for me to think about. So you've got chains and you've got slack in the chain. And then when you pull on the chain, you're increasing everything on the right. It's more like you're alternating between stuff, between chains and slack. So here I have to increment by 5 because I'm incrementing 5 kids. And then I decrement the slack by 1. And then the next time I increment this by 5, and I decrement the slack by 1. And now this is a 0. So now I don't have this anymore. So now when I increment again, I'm going to increment this by 5 and 4, so by 9. How the hell do you formalize this into something that makes sense and is fast? The other annoying thing is that I might have to go through the whole chain. Like I might have n stuff in the chain, and then I have to go through all n, so I'm back to n squared. Unless I can think of a clever way to store the chain as like 2 numbers. I mean, as I'm going, I can combine stuff. So yeah, actually, as I'm iterating through the right side of the chain, I'm only ever looking at one thing, and then I may have to combine it with its thing on the right. You'd never run out of two different slacks at the same time. Okay. Okay. So this pre-computed chain is not helpful anymore. Chain is going to be more like a queue. A stack. It's more like a stack. We add to the front of it, and we merge from the front of it. Okay, so from collections import deek. Kind of gonna start over. So my chain I'll use negative, so I'll just use positive numbers for chain, negative numbers for slack. Chain starts at 0. We're gonna be iterating in reverse order over the list. Which is what we're doing in both cases here. If we're gonna store our total, and we're gonna store the last kid. That's their candy amount. So if, and we're iterating from right to left over the kids. If I, what am I doing here is, if I equals len of ratings -1, so if we're on the last kid, then last kid and total equals 1 and 1. Which actually we don't need to do, we can just do it like this. Are they going to give us a stupid test case where there's no children? Maybe. If not ratings, return 0. Are they going to do that, or can we leave that part out? Okay, they're not going to do that. Okay, so we're starting with the kid on the right, we're skipping that case. Then, if ratings of I, we're doing these cases again. So if ratings of I is greater than ratings of I plus 1, then the kid on the right doesn't need to change. The last kid doesn't need to change. I need this kid to have more than the last kid. and the total. Total is always going to be just add here. So I have one more than the last guy. The total is increased by that amount. Elif ratings of I equals ratings of I plus 1. No consequences for the kid on the right, and I'm allowed to have just a single candy. So did I end up doing this same thing? Oh no, I have just a single candy. So last kid equals 1. Total plus equals 1. Yeah. Else, so now we are adding, the else means ratings of I is less than ratings of I plus 1. Now we need to pop from our chain, basically. So chain.pop left if this piece of the chain, what is that called? Piece of a chain. It's a chain link, right? Links. So this is a chain link. If this link is less than 0, then we've just consumed some slack. Let's not pop, actually. Let's just look at what's in the chain. If there is something in the chain. So if chain and chain of 0, then chain of 0 plus equals 1. We've tightened the slack a little bit. Elif chain and chain just Elif chain. I think chain should start with 0, so there's always something in there. If chain was, if we had slack, we decrease the slack by a bit. Elif chain of 0, or this can just be else now. Else, we're increasing it. And then how do, and then we, hold on, I'm not sure that we're increasing it. The thing I do know is now last kid gets to be 1, total is 1 plus the amount we wish we had given, which is going to be chain of 0. Then chain of 0 goes up by 1. So it goes up every time the kid on the left is less than the kid on the right. If it's greater or equal, then we add slack. So chain dot append left. Is that how you do it? How do you Python from collections import deq of whatever, d equals that, d dot append left 1. Yeah, okay. So we append some slack. How much slack? We append as much as there is a difference between the candy of the last kid and 1. In other words, that. Okay, so we've added some slack to the chain. If the chain slack was less than -1, you increment it. Elif the chain slack is equal to -1, then you pop it out of the list. Chain dot pop left. Okay, I'm also realizing it doesn't need to be a queue if we just append to the right and pop from the right. So this can just be append, this can just be pop. So you reduce the slack if it's negative. You get rid of the slack if you've just turned the slack to 0. And if len of chain is greater than 1, you can combine the last two things. So chain dot append, chain dot pop plus chain dot pop. I don't think you can end up with 2 slacks in a row, because you wouldn't want to do this if you could. Can you end up with 2 slacks in a row? Oh, also, I wanted this to be negative, so this would be 1 minus last kid. But wait, what if the last kid is 1? I also need to do it in this case. So if I'm greater than the kid on my right, then if I'm greater than the kid on my right, then introduce some slack. I mean, actually, the slack is always... The slack is always equal to the amount that you are minus 1. Last kid minus 1, and all of this negated. But only if you're greater... Yeah, I guess if the last kid is 1, then you're not introducing slack, basically. So if last kid is greater than 1, then add some slack, which is last kid minus the negation of this, so 1 minus last kid. We do the same here. Which means we can have multiple slacks in a row. So this isn't necessarily safe, because once we've popped off the slack, we might still have another slack. Unless we made sure we don't have multiple slacks in a row by saying, here, def add slack and amount. Chain dot append the negation of that, and then let's handle the edge cases. If chain of 0 is less than 0, chain of 0 minus I'm not sure that it makes sense to have multiple slacks in a row. I think at that point the chain is broken. There's no height. I don't know. Maybe it does make sense. Let's see. Let's try. Chain of 0 equals minus equals slack else. You append it. Add slack last kid minus 1. If not, slack return. This is getting way too confusing for me to fit in my head anymore. But yeah, you pop the first two things and you add them together. Any chance? Well, no, I'm not returning anything, so return total. Well, okay, yes, that's a problem. Also, what is this else? I still need to do something with the children if it's not an else. So if I'm increasing the slack, I'm still gonna have to say last kid equals 1. Total plus equals 1 in this branch and in this branch. Like, I think I can just do that outside here, actually. Get rid of this, get rid of this. Oh, not that, this. And in this else, not do the plus equals 1, but do the plus equals chain, because we've already got the plus equals 1. We ended up with an empty chain. Oh, wait. I thought I wanted that to not be possible. Can we just start with a 0 in there? Okay, let's try printing I last kid total. So it starts at 1, 1. So we put a 1 on this kid, 1 candy. Then we put 1 on this kid, which is wrong. No, yes, we do want 1 on this kid, but then we want this kid to increase by a chain. So we should have added a chain of size 1. Already. I mean, that doesn't, but it's not, you don't always start with a chain of size 1, right? Do you? So in this case, we skip the 1 and we give it a 1. Then for the 2, it's greater than the 1. So we add slack. Rating of this is greater than rating on the right. That means the rating on the right should never impact, should never be impacted by anything we do from now on. So we kind of want to reset the chain at that point. We don't want to add slack, we want to reset the chain. Nothing we can do will ever matter anymore. Right? 2 is greater than 1. We're never going to have to adjust anything on the right anymore. Okay, so we reset the chain in this case. So we do have to think of the chain as possibly being empty. Okay, so here, let's just run this. Do we still have the right? We probably don't have the right answer for anything anymore. Don't even worry about slack if you don't have a chain. Okay, let's start with this example again. We start with a 2. This kid gets a 1. That happens outside the loop. Then we get to here. This is less than this. So we are in the else case. Do we have to start the chain with 1? Okay, now let's trace through this example. This kid starts with a 1, chain of 1. 1. Left is greater than right, so chain gets reset. This kid is 1 more than the last kid, so this kid's a 2. And the total is now here. Another thing I want to do is let's just put this out here and not worry about setting totals anymore. Yeah, this should be the same answer as before. Okay, so this kid gets a 1. We have a chain of 1. Left is bigger than right. We reset the chain. This kid gets a 2. Next. Left is greater than right. We reset the chain. This kid gets a 3. Next. Left is greater than right. Or left is smaller than right. So we're in this side now, on this side now. You know what? This needs to reset the chain also. Slack needs to be added somewhere in here, but we'll figure that out in a second. Just rerun this. Um, 1, 2, 3. Now we figure out what this does. So left is smaller than right. We're going to give this kid a 1. We're going to figure out some chain stuff. So left is greater than right, which means it's a 1, but we need to add stuff to the right. Okay, basically chain should never be empty. Even in the first time that you add from chain, it needs to be one. You're incrementing the right side by 1. So I don't think we need these anymore. Then the examples are going all over the place as I make changes. Okay, so you're less than the right side. You get 1. We don't have slack, so let's ignore these 2 ifs. And we're going to increase the total, so the stuff on the right, by the chain amount. And we're going to increment our chain amount so that next time we do this, it'll be even bigger. Now, the reason we knew we had to increment it by the chain amount is because the amount of candy on the right, so last kid, is bigger than is less than the chain amount. Something like that. The kid was 1 and the chain amount is 1. So it's that they were less than or equal to, it's that they're 1 less than, no, they are equal. My current chain, the amount that I want to increase the right side by is 1. This is a tough example because there isn't any slack. Did this one have slack? Where was my slack example? One, two, three, two, 1 is my slack example. Well, or 1, 2, 3, 1, 0 is my slack example. What? Okay, we need a new test case because we somehow fixed all the other test cases, even though we weren't done. We weren't done figuring out how Slack works. All right, 2. We have last kid is 1. 5. That's greater than the one on the right. So we reset the chain. This kid gets 2. 4. That's less than the one on the right. So so we need to take a, so you're going to be 1. Then you're going to get incremented by the chain amount. So chain is positive, last kid is 1, and my chain is 1. So I increment by the chain amount. And I increment the chain amount. So if it happens again, I'll be adding 2. And you only had 1 candy. Now we go here again, and it's the same case where this is less than the one on the right. So our chain amount is positive. Our chain amount is positive, so you're going to be you're a 1. The last kid was also 1. Although actually the last kid was also 1. So we're going to be adding our chain amount again, which is going to be 2, and we increment it to 3 for next time. Then we get to 1, that's less again. So we're going to do all the incrementing stuff again. So why doesn't it work? It seems like it should. So this is 1, and then this is 2. And then this is 1, 1, 1, 1, 1. But this gets incremented to 2. Like these get incremented, this gets incremented, and this gets incremented by 1. So we end up with 1, 2, 3, 4, 1. That would be 1 plus 2 is 3, plus 4 is 7, plus 1 is 8. So I'm outputting 8, it's expecting 11. Expecting 11? What's wrong with my allocation, which is 1, 2, 3, 2, 3, 4, 1. You have higher than your neighbors. You have higher than your left neighbor. You have higher than your left neighbor. Oh wait, I summed this wrong. This is 6. This is 10, this is 11. So I am expecting 11. According to my tracing, I thought I was going to get 11. So 1, 2, 1, 1, 1, that is what I wanted. 1, 2, 1, 2, 1, 2, 1, 1, 1. And then I tried to increment by 1, increment by 2, increment by 3. Yeah. Increment by 1. So 1, 2, 1, 1, 1 is 1, 3, 4, 5, 6. And then increment by 1 is 7. Increment by 2 is 9. Increment by 3 is 11. Okay, so what I thought I was doing should give the right answer, but it's not giving that, so I have a regular kind of bug. Oh, at this point, last kid is not less than chain of 0. But we also don't have any slack. Like if this were an else, and like if this stuff didn't exist, because I'm not sure how to handle slack yet, this would give the right answer on this test case, 1, 3, 4, 5, 2. it's not giving the right answer. So it's still 1, 2, 1, 1, 1. 1, 2, 1, 1, 1. I want to print plus chain of 0. Chain of 0. I'm only adding the, oh wait, wrong test case. So 1, 2, 1, 1, 1, plus 1, plus 2, plus 3. Doesn't that give 11? Python. 1, 2, 1, 1, 1, plus 1, plus 2, plus 3. Oh. Uh, 1, 2, 1, 1, 1. And then I apply the chaining 3 times, which I thought would be what you would want to do here. So you say this is a 1, because what, okay, so what would you end up with? 1, 3, 4, 5, 2, you'd end up with, you start with this. This is the allocation just going from right to left. And then you have to add the chains. So when you're on this one, you say it's a 1 and you add oh, there is supposed to be slack here actually. The first one you weren't supposed to add because there was supposed to be slack. So after the first one, you end up like this. Basically, it's like this one, this one is the same no matter what. Then you add a 2 because it's bigger than its neighbor. Then you're going to add a 1, and you're going to respect the slack and not add an extra 1. Then you're going to add a 1 and increment due to slack, or due to the chain. And then you're going to add a 1, 2, 3, 4, incrementing because of the chain. So we needed to add a slack here. So when 2, because the number is bigger than 1, we need to add slack. Anytime last kid becomes bigger, we need to add slack. Add slack. We're just adding 1 slack. Adding 1 slack. Actually, I don't know what to do when they're equal. We'll come back to that. To do handle equality. Did they tell us that they can be equal? Yeah, some of our examples have them equal. Yeah, so we'll figure out what to do when stuff's equal. Okay. Now, if there's slack, you increment. Yeah, so if there's slack, you increment. So if there's a bunch of slack, you increment it by 1. If the slack is going to go away, then you just pop it. Let's not worry about merging. And then the only time you add slack is elif chain of 0. So this is else. So there is positive, not slack, but like stuff. There is a chain. Then you add the chain amount. Okay, and then, oh, but I did add slack over here. I don't want to look at chain of 0. Oh, everywhere where I'm doing chain of 0, I need to be doing chain of -1. Because I forgot I changed the queue, or I changed it to be using a stack, so the stuff goes on the right. Okay. This is more like it, but the issue is I started at 1 and 2 when I meant to start at 2 and 3 and just skip the 1. So in this case, even though I skipped the slack, I still want to increment the chain. So that kind of makes me think, is it possible that this is not a stack and we just have one int for the chain amount and one int for the slack amount? So it's like chain equals 1, slack equals 0. I don't know what to do with equality. We'll figure that out. Then if we have slack, we increment it. There's no such thing as popping, so it's not even if slack, it's just so we want to reduce the slack. So if slack is greater than 0, slack minus equals 1. This should be slack plus equals 1 because we're adding slack. I don't know what we're doing here. I think we're resetting. And I don't think we're touching the slack. So this might already work. If we have slack, we get rid of it a little. Otherwise, but we also increment the chain. So I think we're incrementing the chain unconditionally here. Something like this. That did what we wanted. We skipped 1 and we skipped 2. I'm guessing the equalities are the ones that are... No, this one has no equalities, and these are both the same test case. We don't need both of these. Okay, so here's what I think we should do when we get this. So we start with 1. Then left is bigger, so this becomes 2. Then left is bigger, so this becomes 3. Then left is smaller, so this becomes 1. But due to slack, we did not increment. And then this becomes 1, and we did increment. Actually, this makes it look like we're going to need a stack after all. Because then if we had another one, we would want to increment it by 3, not by 2. In this case, we never thought we had to increment at all. We never added any chain contribution. We're missing that +1 for some reason. So it goes 1, 2, 3, and then 1, and then there should be no incrementing. Slack's not plus equal 1 here. Slack is equal to last kid here, I think. We broke this case again where you go, we're missing the +2. Here the slack should only be 1. It's -1, right? Because the slack is the difference between the amount of candy on the one on the left, which is going to be 1. Okay, so now back to this case. We're never doing any chaining. So 1, 2, 3. So at this point, chain should be equal to 1. Then here we get to the thing on the left is smaller. We don't have any slack. We actually do have slack. Thing on the left is smaller and we have 2 slack. So we decrement the slack by 1. It looks like, okay, we decrement the slack by 1. We do not add the chain. Then we increment the chain by 1. Okay. This really makes me think we need the stack. Because this chain gets incremented. The slack got decremented, but only by 1. And then when we get to the next 1, because there's still slack, we didn't increment at all, but we should have incremented by, there shouldn't be slack between this and this. There's only slack between this and this. Where this is this one, 1, 2, 3, 1, 0. Yeah. Okay, we need to go back to having a stack. Oh my god. Slack's not something you can add to the end. Well, in a way it is actually. No, it's not. Slack needs to be inside the queue, inside the chain. So what should the chain actually be at this point? This is so confusing because the chain kind of always needs to be 1 when it's reset. This should be resetting the chain, but it's also introducing Slack. So this resets the chain, but it also introduces Slack. Though the Slack, yeah, it has to introduce Slack. So yeah, there's a 1 hidden behind this amount of Slack. Equality, I don't know how it works. I'm gonna treat it the same way as this for now. If chain of -1 is less than 0, then reduce the Slack. Otherwise, increase the amount. And then this thing, what is... When do we increment the chain? It's when we always increment the chain. But how do we know which ones to increment? I think everything in the chain, that's positive should go up by 1. Which is going to make this be a for loop again, which is going to be slow. But for j in range of len of chain, if chain of j is greater than 0, chain of j plus equals 1. Does everything in the chain go up by 1, or only the... This is equality, so that's too hard to look at. These are confusing because I don't know how I broke them. Does only the stuff before the first Slack... It might actually be only the stuff before the first Slack. Yeah, because going up by 1 already means you're adding it to all the stuff that you're incrementing. Okay. But the problem is now I'm not going to be able to skip 1, which is what I need to do. There's no J, chain of. I managed to skip 1. I'm not sure. That is what I wanted, but I don't know why it's working. And why aren't I getting the right values? This one's supposed to be one, two, three, two, 1. I'm adding too much stuff here. The chains shouldn't be triggering like this. So this should be 1. And then you are 2, and then you are 3. And then you go to the else. We have slack. So I'm incrementing the slack. And I'm setting myself to 1. That's right. I forgot to do this. If chain of -1 equals 0, then pop it off. But why am I adding 2 here? Oh, I'm not. This would be the right number to look at. Okay, so let's look at this one. I'm adding 1 and then I'm adding 2, but I shouldn't be adding the first one. 1, 2, 3. And then it thinks I should add a 1 here, but I shouldn't because I should have some slack. Oh, I'm doing this in the wrong order now. I forgot my chain is facing the other direction now. Okay, that's what I wanted for that. That's equality. Okay, we're adding 0. That's weird. That shouldn't happen. How could this be 0? Whenever it's 0, I pop it off, and I never set it to 0. Oh, last kid could be 1. Last kid could be 1, which would mean I'm a 2. Which should mean there's a slack of 1. So I think I meant to do this after setting the last kid. I just keep getting farther. One, 2, 3, 1, 0. I can't believe how hard this is. It's just driving me crazy with all the like, I don't know how I've been able to make so many mistakes in so little code. It's because it's so abstract. Okay. 1, 2, 3, 1, 1, and it's supposed to be 1, 2, 3, 2, 1, and that would give you 9. I'm not adding a chain where I should be adding a chain. So let's take a look at, once we're at here, then we should not add a chain because there's slack. So we should go chain of -1 is negative. So we increment it and now it's 0, and then we're going to pop it off. Then we're going to set last kid to 1. Then over here, we are less than the one on the right. So we're in this branch. We don't have slack anymore because we just popped it off. So we're not in this branch, we're in this branch. We should be adding chain of -1, which should be 1. Why don't we print at each step what the chain is. So here the chain is -2, and then it's -1, and then it's popped off. So I think I'm just setting my slack too high. Because it's like, if you're a 3, that means you have enough slack to skip once. So this should kind of be 2 minus. But that is going to make it sometimes positive, which makes no sense. Chain equals 1. Chain dot append this. Okay, now in this case, I'm supposed to go, okay, we have this example written, right? No, we don't. We've never traced through this example. Let's do that now. So we start with 1. Then this is larger, so we add a 2. Then this is smaller. So we add a 1, and we don't increment this because there was slack of 1. So chain needs to have -1 here. And then chain can be popped off here. So we didn't add anything. -1, but it has a 1 hidden behind it. And then here it's down to 1. We popped off the -1. Now we add a 1 here, and we're going to have to increment both of these. So I guess when we popped off the -1, we should have incremented the chain also. Or is we should have, yeah, we should have incremented the chain, because incrementing the chain just means we're moving left and there's going to be more stuff to increment by. So we popped off the 0, but we should also increment the chain. Does that make any sense? I keep running into the same conflict where sometimes what I think I need to do is increment the chain, and sometimes what I think I need to do is not I guess I don't know why I wouldn't increment the chain. So let's look at this again. This one again. 1, 3, 4, 5, 2. No, let's look at this one that we already had working before. Now we're adding 2, but we should only be adding 1. We moved left. So the chain has something here. It got incremented when we moved left, even though there was enough slack not to have to do anything. And then when we moved left again, we added our chain, which was too big. I guess here we should have added in this example, when we moved left in the last spot, we did not increment the chain. But it's kind of like our chain is supposed to have kind of like a 1-1, because we have the slack in between. This is so confusing to me. I would definitely benefit from a break, but I'm going to try to power through. If we're picturing our chain here, okay, what is a chain? A chain is adjacent numbers in increasing, not just increasing, but in +1 order, like where each one's one more than the other. Of candy. So if I have 1, 2, 3, that's a chain where I'm gonna have to add 3 to it. If I have 1, 2, 3, 8, that's a chain where you need +3 for a while, then +4 when you get over the hump, over the slack. So you would need 3 here. If the next thing is a 1, then you need 4. If the next thing is a 1, then you need 5, but you're not adding this. But you know that there's more on the right once you get through the slack. Can you ever have more than one thing of slack? Like, could I have this? No, not really, because the reason that this would have to be 8 is if it's one more than the thing on the right. So you can't have chains with slack within them, I think. I think you can only have one slack. Yeah, because the thing on the right of the slack needs to be smaller than 8. It couldn't be like, then you have 9, 10, 11. Because there would be no reason for this to be 8. Okay, so a slack in the chain is only ever hiding an extra 1. That's important. So you really only need 2 numbers. There's like the current chain amount, the current slack amount, and then once the slack gets to 0, that just increments your chain by 1. Okay, what if, is that true? Because what if you have 1, 2, 3, and then here you have 3, 2, 1. Yeah, I think the chain gets broken, but I also think I'm mixing up ratings and candy. Here I've been talking about candy. Allocated in the order that I've been allocating it. Does this make sense? Yeah, it makes sense. And it's what you would get with, this is the same for, this is the same rating and candy. Or with these ratings, you would also assign these candy amounts. So is there more stuff on the left we could add that would need us to continue this chain? No, it gets 100% broken at this point because this is saying you need to be bigger than the thing on the right. So even if this gets to 1,000,000, that's not going to affect our chain on the right. So okay. I think we only need 2 variables, chain and slack, and when slack gets to 0, that only increments chain by 1, by like an extra 1 than we expected. Okay. Chain and slack are back to being numbers. You have a certain amount of slack. And you reset the chain whenever you are bigger than a number on the right. When you're bigger than a number on the right, the amount of slack you have is equal to 1 minus the amount that you are. We can count this chain as 0. We just need to know that once the slack runs out, you add 1. I'm not positive about that. But let's try that. No, well, I'm not sure. I'm not sure. Let's see. I've still never thought about equality. We'll have to get to that soon once we've solved our non-equality bugs. All of this stuff is a mess. If slack is greater than 0, then we get rid of some slack. If slack is equal to 0 after that, then we get a bonus +1. Not to last get, to total. So whenever we run out of slack, we get that extra 1 that was hiding behind the slack. No matter what, chain goes up by 1 and total goes up by chain, though I think that's in this order. Let's print our chain in slack and see if it makes any sense. So we did 1, 2, 1, 1, 1 for allocating our candy, which is right. Then at this one, we basically never added anything from the chain, and that doesn't seem right. So 1, 3, 4, 5, 2. Oh, it's because I'm mixing the negative and the positive slack. Slack's not supposed to get negative. In my last solution it did, but here chain and slack are both positive. Okay, so 1, 2, 3, 1, 0. Let's print added our slack 1, and let's print plus chain to see when are we adding stuff from the chains and from the slacks. So 1, 3, 2, or I don't want to look at that one. 1, 2, 3, 1, 0. We added a slack 1 and we added 1 from the chain. 1, 3, 2, 1, 0. What we wanted was to only add 1. So I think our slack 1 should not immediately go into the total. It should go into the total next time. So if we just do this at the end, this should just increase our chain, not our slack. No way. I mean, there's no way that this works because I didn't handle equality. Unless this is like the right thing to do. I guess it is. Oh my god. This was the craziest one ever. Just none of this ended up mattering. The only thing that mattered was we're still so far on the right. We're still so far. This was the worst day of Leetcode ever. Everything we did was like the worst possible solution to everything. How can this be slow? It's O of n. We're only going through the list one. Okay, it's not slow. Okay, good. It's not slow. Okay. Just looking quickly to see if there's anything we can do to speed things up. I don't think so. This looks pretty much perfect. We're just looping through one time. We've got this insane system for counting the sum. Yeah, it's just madness. Is this really what other people did? Like, 2 pass. I don't have 2 passes. Oh, okay, 1 pass is their second version. Up, down, peak. I think this is doing what we're doing, but I don't understand their variable names. Probably if I read their explanation, it would make sense. It looks like it has a lot in common with us. They're just like assigning all of their variables at the same time. They're using some 0 for things that we would have counted as 1, and doing this the way we're checking if something's equal to, when something gets to be equal to 0, they're converting a Boolean to an integer here. So I think they're doing what we're doing, but just in a really hard to read way. Incredible. They're calling it up, down, and peak also. It's the 2 pass and the 1 pass. Yeah. Okay, I think we discovered the same thing. They're literally doing the same thing as the other person. I wonder if people are copying each other. Well, one thing you know for sure is I didn't copy this. I came up with this through blood, sweat, and tears with a completely different way of thinking of it, with a chain and some slack. Anyway, cut me some slack if this was helpful, and give me, upvote me, please, on Leetcode, or give me a +1, or give me a thumbs up on YouTube. If this was helpful, thank you so much, and that's it for me.